Hello, everyone. Good evening, good morning, good afternoon, but most of us were having Asia. So good evening, everyone. So let me share my screen first. Okay. Hope you can see it now.
Yes.
Okay. So thank you, iLEAPS, for giving me a chance to talk about this topic. So I would focus more on atmospheric emission and impact on ecosystem, and mainly in mainland Southeast Asia. So my talk highlights that first I would give an overview of atmospheric emission and potential effects on ecosystem, and then a little bit on status of acid deposition in Asia, and then we go to the current and future atmospheric emission in Asia, and then atmospheric deposition in mainland Southeast Asian countries. That is the focus of our projects, and give a summary and key messages. Let me see. Okay. Now, atmospheric emission and ecosystem effects. So when we talk about atmospheric emission, so we normally start with first emission. So where it come from? It come from power plants, man-made sources, so transport and biogenic or natural sources. And then once it is in the atmosphere, so it participates in chemical reactions to form secondary air pollutants and also diffuse and transport in the atmosphere. So some of them are going to long-range transport, but some of them actually participate in the cloud chemistry and become washed out with the rain, so it can wet deposition and rain out, wash out, give you wet deposition. Some of that actually deposit dry, it's dry deposition. And when you go to the on the Earth surface, it causes effects. So effect, we talk about an air pollution effect on human health, and then we talk about effect on plants and aquatic lives. So, and the materials. For ecosystem effects, we talk about the direct effect of the phytotoxic air pollutants and effects through the atmospheric deposition. So talking about direct effects of air pollutants, so we have normally listed list 5 most influential air pollutants for plants and trees. The first one is ozone, very actually important. Secondary air pollutant, it in gas phase and it forms in the photochemical reaction in the presence of sunlight and involving the precursor of NOx and hydrocarbons. And it is one of the most phytotoxic air pollutant of concern today. SO2 have primarily emitted from combustion of fossil fuel and it in the gas. So the sources for man-made, mainly fossil fuel combustion. We talk about mainly in power plant, like power generation, industrial activity, and some transport activity. NO2. Actually, and the emission actually NO, but in the atmosphere, it turned to NO2, so that it could consider like secondary, but primarily also emitted NO2 in gas phase, and it comes from mainly motorcycle in the urban area, and also some from fertilizer production. Then we have HF, so that fluoride compounds. It are primarily emitted, and then it have maybe in gas and particle phase, and mainly come from superphosphate production, aluminum smelters, briquettes, which is very popular in Asia. Ethylene, so it's also primary pollutants in gas phase. So man-made sources, it comes mainly from combustion, but we know that it also naturally emitted from soil, ethylene. So effect of this air pollutant in the plant, you can see SO2 effects by killing the tissue on the leaves, make leaf scatterize. It means it's scattered here, the SO2 effect. For fluoride effect, you see the burnt of the lip tip, like this. So, and then when we talk about ozone effect, so it like dead tissues of the lips that flex on the upper surface of the lips. So this is the effect by ozone. And for ethylene effects, actually it causes early ripening of fruits because some fruit dealers may also use ethylene to make ripe earlier. But naturally, if we have this fruit, it's in very young guava here and it's getting ripened, so it damages the fruit actually. The quality of the crop would be reduced substantially. Now, example of ozone effect on crops. So here on the right, you can see the growth of rice plants when exposed to different level of ozone. If it exposed to lower level of ozone, lower than 10 ppb here, we see the biomass in of the rice is quite significant. But when it's exposed to ozone at 90 ppb part per billion, right, then we see that it affects on the growth of plants significantly. Now, in one of our experiments conducted in Vietnam by my former master student here, so we try to have rice species in Vietnam exposed to ozone at different level, 7 hours per day, and using open top chambers. And we can try to see that how this exposure to ozone affects the yield. And here, upper line, you can see the inch of the straw. It means the biomass, dry mass. And lower line here is the inch of the grain. It means the actually in of interest here. And you can see the declining trend here. The higher ozone the rice exposed to, the lower the inch. And we estimated that for every 10 part per billion ozone increase, the rice grain inch would reduce around 4 to 0.5%. That significant reduction. So now talking about effect of atmospheric deposition or acid rain here, and talking about acid rain chemistry. So you can see that emission, for example, here come from power plant, we have NOx and SOx emitted. So we have sunlight providing energy for all these processes. And it's forming ozone here, ozone acts as catalyst to actually oxidize, okay? Sulfur dioxide and nitrogen oxide. And in the atmosphere, with water available, it forms sulfuric acid and nitric acid. And this actually acidic, when we have the cloud formation, so it incorporates in that process and it involved in the clouds. And when it rain out with the clouds and with wet deposition, and the wet deposition in under rainwater, you would find ammonium nitrate, sulfate, and H plus here, iron. So it have dry deposition in terms of gas and in terms of particles that containing NOx and SOx. So when we talk about ammonia, that is very important role for neutralizing this acidic species. So it comes in Asia, it comes mainly from agricultural activities like using fertilizers and livestock, but it also have natural source. So major acidic species found in rainwater include sulfate, nitrate, ammonium, chloride, and formic acid. And formic acid actually natural, is believed. The sources I mentioned already. So in the polluted air, the atmospheric lifetime of NOx and SOx is around a few hours to days. And it cleaner air, it will lasting for long, but it's very polluted air, and especially when we have high ozone concentration, it will be very fast oxidation would occur. So talking about the effect of acid rains on the ecosystem. So first, acid rains, because if acidic species deposit, it would acidify water bodies, surface water bodies. And then for terrestrial ecosystem, actually it causes plant and tree deaths, okay? And it causes damage to forests in these two pictures. And of course, when water is acidic, so fish cannot survive and the fish dies. Now, talking about mechanism of effect of acid rain on terrestrial ecosystem, detrimental effect occurs when pH actually below 3. And how it occurs that how it disturbs this is on the soil and the plant cause plant damage. So looking at acid rain, when it acidic species deposit and then go through the soil here and soil layer. So with low pH, so it could help the metals actually in the soil could be dissolved, and then it leaching out of the metals. So it caused the upset of nutrient balance of the soil. And low pH also kills or eliminates some useful soil organisms. So for the plant, yeah, here I also got from a presentation of notebook, last notebook. So she said that plant in a different pH. So when pH is 3.0, then compared to tap water pH when for irrigation, you can see that, okay, in the tap water, the growth of plant is more significant than pH is 3.0. So in general, the acid deposition would cause direct damage to leaves and then growth reduction, increase seedling mortality, and reduce resistance of plant to pathogens. And overall, it will reduce the forest and agricultural productivity. Now, effect on aquatic ecosystem. The detrimental effects actually occur when pH falls below 4. This is because acidification, acidified surface water bodies like this would enroll or induce biological and chemical changes in water body. So it changes in flora and fauna diversity. Some species that like acidic water would survive and thrive, and other species may die. Overall, if we talk about the species loss, here on the upper corner, you can see here, this is pH from 4 to 6 something, and this is loss, okay? Loss, not gain. So at 4, no fish species, that means 100% loss. And for benthos and zooplankton, so only some of them survive. So this is higher, the lower the pH, the more the loss. And when pH getting higher, water is less acidic, so we can see more species again here. So for the earlier we talked about the release of toxic metals. So when from the soil, so it released aluminum, mercury, lead, or whatever. So in the soil, leaching out to the water. And it appears that aluminum is very toxic, and it's most toxic at pH in the range from 4.5 to 5. So it causes fish death, like this. Okay? So overall, it result in aquaculture and fishery loss. So because the low acidic water would prevent fish eggs from hatching, it causes damage to fish larvae, and it lower immunity factor in adult fish. So the severity of the damage depending on buffering capacity of water bodies. Now, it also have other effects, like effect on materials, like the monuments that affect by acid deposition and other also weathering effects, I believe. Effect on human health actually goes through methane leaching to water resources, and heavy methane would get bioaccumulated, magnified through the food chain, so it have chance to get to our body. So it also have effect on atmospheric composition. It's more acidic, and so we have also visibility because sulfate and nitrate particles are fine particles. It actually disturbs it affects visibility considerably, and it also have climate impacts. I am going too fast. Are you okay? Okay. So assuming that those just introduction, right? Now we talk about acid deposition status in Asia. So here I take a picture from Webb et al., published in 2014, and show here ensemble mean patterns of total deposition of nitrogen in kilogram or per hectare per year, and back in 2001. And we can see also darker area here over Asia. So India, Bangladesh, China, Vietnam, Southeast Asia here in this region, the hotspot. So in terms of sample, you can also similar picture, and a lot of that in China region here, back in 2001. Of course, right now it's on the change. Also, we still see that Asia is in global hotspot of nitrogen and sulfur deposition. And then we can see some part of here, we have high deposition. Now, the acid deposition status in Asia is also being monitored by ENET. The ENET stands for the East Asian Acid Deposition Monitoring Network, and this is as of 2021. This is a station available in East Asia, but you can see also include some station in Russia, some station in Mongolia, and a lot of station in Japan, and also station in Southeast Asia here. And then station include urban site, rural site, and remote site. So rural, urban, rural, and remote site, the detail of monitoring is described here. And then for the remote site, or there are some sites also selected for ecological survey. So it's survey of the soil, forest, and inland aquatic environment, so that it's happening. Now the result of ENET from the raw data we got from the website. So my staff helped to make this charts. So you can see here we selected for a few countries: Indonesia, Thailand, Vietnam, and other countries in Southeast Asia. In Indonesia, we can see the station name here: Jakarta, Serpong, Kota Tabang, Bandung, Maros, Jambana, and Lombok. And we see that the range of pH actually from 4.5 to 6 from 2000 to 2021. So the range of is that. And then recently we can see some of the decreasing trend here in some stations, and one station have very high level increase. So in Thailand, we can see the station, 6 stations available, and 3 urban and 2 rural, and 1 is the remote side. And the pH is range from 5 to 6, and then there are some also decreasing trend here, but it's fluctuating a lot. So in Vietnam, the pH also in the range from 5 to 6, and station in Da Nang, you can see pH decline, and also in Hanoi, it declined recently. For other countries, we can see the range is from 4.5 to about 7. Like one station is in Cambodia here, the level is quite significant. We also have a station in Myanmar, Yangon, the pH is quite high, 6.5, right? Now talking about the emission and post-emission trends. So this is taken from Nguyen et al. So showing global SO2 emission by region. Okay, and you can see here beyond 2000, because it's a very large scale, like 2005 something, the data, and then East Asia, this is the level trend shooting up. Okay, and then we have Southeast Asia. This is blue light. We also have India, this slide. So we see the increasing trend in Asian countries, while in Europe and North America, they have a declining trend since the 70 something, the strong declining trends of the emission of the SO2 emission. Now looking closely in some country in Asia, you can see that China emission increased from to 1990. So, and increase SO2, and then up to 2005 something, the country take action and SO2 reduce. One, we help the NOx emissions didn't increase, and ammonia emission like stable, slightly declining here. In Japan, we see also as NOx emissions is high, but it's reducing, and all others like SO2 and ammonium also declining. For the Southeast Asia, that focus, so all three species increasing. Now, atmospheric emission and deposition in mainland Southeast Asia, or we can also call Greater Mekong subregion country. So this is actually our projects, AAT project that we conducted, and it called that atmospheric deposition to large river basin and potential effects on the water environment. The project period is from 2020 to 2023. Though we got some delay because of COVID, but right now we are ending at the ending stage. So this is our domain. So mainland Southeast Asia or Greater Mekong subregion or Indochina, including these countries, 5 countries: Myanmar, Vietnam, Laos, Cambodia, and Thailand. So that is country. So we also focus on this own GMS domain, and then also with focus on urban area of Bangkok, Phnom Penh, and southeast region of Ho Chi Minh City of Vietnam. So 3 domains. We conducted emission inventory for the key species like SOx, NOx, CO, non-methane VOC, ammonium, PM10, PM2.5, black carbon, organic carbon, and key greenhouse gases of CO2, methane, and nitrous oxide. So from that emission data, we also conduct the WAP CAMEX simulation and to assess water, air quality, and the deposition. And then we have all the outer domains and inner domain. And then inner domain, urban domains, we aim at 2 by 2 square kilometers for the emission and also for the simulated results. The project is sponsored by SIDA, Swedish SIDA, and coordinated by Summernet Network of the Stockholm Environmental Institute, actually in Asia. And we have another partner in Nông Lâm University of Ho Chi Minh City, and we here AIT, Asian Institute of Technology. It has a few objectives. The first objective is to assess the effects of atmospheric emission on the deposition inroad to the large GMS river basin. The second objective is to quantify multiple benefits of the air emission control, like under emission scenario, like RCP or IPCC, to the river water quality, to the ecosystem, to air quality and climate. And the third is to provide science-based information to policy making. And the method we use here includes monitoring, modeling, and local survey of the communities in the basin who are affected by the emission and acid deposition. Now, the key finding of the project from IIT side, the first, we have the emission inventory conducted for mainland Southeast Asian countries, including pollutants and greenhouse gases for the base year 2018. So we have emission scenario for mainland Southeast Asia under business as usual, under RCP 8.5 and RCP 2.6 for 2030. And then we conducted WAP CAMEX simulation to produce atmospheric deposition fluxes in 3 urban domains of Bangkok, Ho Chi Minh City, and Phnom Penh. So for the Myanmar or Bangkok domain, we also put a little bit more efforts by producing critical load and try to see the potential impact of acid deposition on the ecosystem in the domain. So project also conduct assessment of impact of acid deposition on river water quality in Chao Phraya River in Bangkok and in Labuang River in Ho Chi Minh City. And we conducted question surveys for selected communities in Bangkok and Ho Chi Minh City. So we have dissemination workshop. We have 2 nation workshops in Vietnam and Thailand. We also have an international workshop at IIT. So we produce policy brief and that in English and translated into all 5 nation languages of mainland Southeast Asian countries. Then we also at university researcher, we produce a paper, peer review publication. Now for the emission inventory, so when we conducted emission inventory, we covered this key source sector. And some of you, maybe all of you already know what is emission inventory. I just go briefly through here. Emission inventory is a compilation of the emission from all these sources, okay, by conducting activity and using appropriate emission factor and put it together and have a database. The sources we normally cover is point source, area source, non-road source, on-road source, and then urban burning to combine together. In this study, we actually conducted emission inventory covering transport on-road and transport off-road, like railway, aviation, inland waterways, and agricultural machineries. We have industrial combustion and manufacturing processes, and we actually also have a little bit more focus on thermal power plants in the region. And of course, we include biomass urban burnings, like crop residue urban burning, forest fire. So we also have residential and commercial combustion, and then waste management and waste urban burning too. So this is the results. Here show total annual emission in 2018 and shared by country. The upper row here, you can see the value, and that is total GMS emission in gigagram per year. It means 1,000 tons per year, the number here. Okay. For example, for SOx emission in 2018, we have 1,499,000 tons in that year emitted. And looking at by country, so you can see the red color here is Vietnam, strip here is Thailand, Myanmar is blue, and Laos is yellow, and Cambodia is also blue bone here. So at a glance, you can see that Thailand and Vietnam, actually the key country contributing to the emission. So, and then in Cambodia, the emission of some species is higher here, like organic carbon. Okay? And in Laos, emission is quite low. Myanmar is fluctuating with some species is low and high, but basically Thailand and Vietnam are actually the key contributors. And acid rain precursor, as I mentioned earlier, include SOx, NOx, and ammonia. So the key precursor. Now, talking about its share by source sectors across all 5 countries. So which source contribute most? It depends on the pollutants. So, for example, taking PM2.5, they mainly come from biomass burning, right? Forest fire, crop residue open burning, municipal solid waste open burning. And then you have transport, on-road and off-road. And we have the purple color here is residential and commercial combustion. And here the red color, industry is yellow, and red color, we can see it thermal power plant. But for sulfur dioxide, for example, thermal power plant can contribute the most significant. For CO2 emission, thermal power plant, open burning is a key sector. For CO, actually, open burning is key sector. And methane here, actually residential and commercial combustion, because we did not include the methane from rice paddy. So see like that, and then black carbon. So overall, the transport, urban burning, industry, and thermal power plant are the key sectors contributing to pollution in mainland Southeast Asia. Now, we attempted to project the emission under different scenarios. So we use RCP, it's representative concentration pathway, 2.6 watts per square meter, okay? And representative concentration pathway, 8.5, and try to project it to 2030 and compare it to the base year 2018. So we can see here the 2018 and here the 2030 under the RCP 2.6 and here 2030 under RCP 8.5. And we can see that most of pollutant increase, okay, in both of these scenarios, higher than 2018. And of course, more increase expected for RCP 8.5 because it is less control. With RCP 2.6 is more control. So only one pollutant, you can see some reduction in RCP 2.6 is SO2, okay, by 14%. Now, in terms of greenhouse gases, so we can see that by 2030, under RCP 2.6, so greenhouse gas emission reduction observed for all 3 species. Under RCP 8.5, as expected, so emission of greenhouse gases increased by from 12% to 27%. Okay? This is 3 of them. N2O, methane, but to be visible, we multiply by 100 here to see, and CO2. Okay. Now, spatial distribution of NOx and SOx and NOx emission in CMS country, and this is spatial distribution made by 2 by 2 square kilometers. And this is not very clear because everything is yellow here. I'm sorry, it should be from green to yellow. Now, this is, we can see here the darker color seen over Hanoi, Ho Chi Minh City, Bangkok. Okay, so, and this is also urban area down here, and Thailand, this is great. And for NOx emission, we see similar picture. The higher emission intensity observed over the urban, more concentrated activities, human activity area. So we have a little bit for more focus on emission from thermal power plant, and my PhD student just published this paper. So here we have the emission of thermal power plant, and this is, you can see the estimate of emission of the best estimate, high estimate, and low estimate. So of different species here. But to more clearly, you can see here annual emission in gigagram per year, and for CO2 in teragram per year, right? Emission inventory design we made for 2010, 2015, and 2019, and projection until 2030. And here projection we didn't do follow the RCP scenarios, but following the nation power development plan. So it means actual plan, that master plan that each country in the GMS follow. So we can see the emission increase over the year, and it keep increase projected until 2030s. And for all species, we see increasement. Only methane, we see some reduction here. Okay? And this is actually related more with the structure of the fuel used in the power plant. So if we look at the emission per fuel types, so we can see here we consider 3 types of fuel: coal-fired power plant, oil-fired power plant, natural gas-fired power plant. And you can see here SO2 emission. So coal actually contribute most of SO2 emission, right? And then oil. And back in 2010, we have more oil-fired power plant, but at present we have less oil-fired power plant. And then in 2013, we also did not expect to have too many oil-fired power plants. So for NOx, actually divided with coal and natural gas. And similarly for PM2.5, more from coal-fired power plants, okay, CO, and non-methane VOC. Only ammonium actually appear to be more from natural gas-fired power plant, a little bit higher than coal-fired power plant in terms of share. Now, I want to focus more on the acid deposition. So try to see if any relationship between the annual thermal power plant emission of NOx and SOx in different countries of Southeast Asia, mainland Southeast Asia, and we plot it here in a bar, okay? Every year emission, okay, in the bar, and the emission rate here, gigagram per year, 1,000 tons per year. Yeah. And then we also plot the results of the concentration of sulfate and nitrate at selected sites, okay, at selected sites from the iLEAPS study. The here selected is Phnom Penh site, Yangon site, Bangkok site, Hanoi, and Ho Chi Minh City. So you can see the emission trend look like this, the bar, right? Looking from this Y2 axis. And then here the millimole per liter, it means the concentration of sulfate in the rainwater. So you can see very clear increase in Hanoi site. Okay? And Hanoi actually located downwind to a few large coal-fired power plants in the northern Vietnam. And when the wind blowing the northeast monsoon prevails and more polluted season, actually the wind will blow, bring in the transport of the SO2 from about 150 kilometers away to Hanoi site. So we also see the increase in Ho Chi Minh City side, some decline trend in Bangkok, and in Phnom Penh we have data until 2017 only. And in Yangon, also a little bit stabilized here in terms of sulfur dioxide emission in relation to centric concentration in rainwater. So on the right side, you can see this is a similar figure, but actually for nitrate concentration in rainwater. And we plot also emission of nitrate from thermal power plant. And we also see very strong increase of the nitrate concentration in the rainwater measured in Hanoi. Okay? Of course, we cannot rule out the long-range transport emission far away outside the mainland Southeast Asia to the domain and also other sources. But at least we see some perhaps suggesting that a thermal power plant actually contributes significantly to the acidity of the rainwater measured at the site. In terms of the atmospheric deposition in urban area that simulated by WAP-CAMEX of our study. So you can see here the study domain of Bangkok, Ho Chi Minh City, and Phnom Penh. The sulfur deposition flux in terms of kilogram per square kilometer per year. And you can see this is dry deposition, wet deposition, and total deposition. So the higher deposition actually intensity, we found it for Bangkok, where we also have higher emission intensity. And second is by Ho Chi Minh City, and third is by Phnom Penh, which is really following the ranking of the emission intensity in these three domains. For nitrogen deposition, we can also similar trends. And actually in Ho Chi Minh City, the deposition is quite high here. And the wet deposition is higher than Bangkok, but dry deposition is lower than Bangkok. Okay? And we try to also separate the total ammonium deposition flux, ammonium only, that includes both gas, ammonia, and particulate matter ammonium, that because modern produce deposition for different species. And here the range is around, say, 10% of the, or a little bit more than 10% of the total nitrogen deposition fluxes. So looking closely to the spatial distribution of simulated acid deposition in Bangkok and at 2.2 square kilometers. So we can see here in the domain, if we look at the, if we add the emission, deposition when all the grid in the domain, the total deposition accumulated would be 8.23 gigagram per year deposited per year in the domain. For nitrogens, the much higher is domain-wide. You take the summation of all these grids, so it would give us 23 gigagram per year of the nitrogen deposition. And this is graded, you can see very large in the urban area. While the sulfur is more scattered and showing the thermal power plant and also industrial activity. Now, to assess potential impacts on ecosystem in Bangkok, we try to use critical load approach. And for critical load approach, we first calculate the critical load of acid deposition using material balance approach. And one of my students who also in this audience that made this map for critical load. And then we also use a detailed land use map and simulated wet and dry deposition from WAP-CAMEX and try to overlay it and find out, mapping out accident map of acid deposition. Let's look closely. First, critical loss of acid deposition determined. Okay, and it appears that the area in this corner, the green here, green color, have low critical load. So critical load by definition is kind of tolerance. It's the maximum the deposition that this ecosystem can tolerate. So lower critical load is higher vulnerability of the area. So we can see here critical load of sulfur in BMR. So the range is from 589 to 1,600 equivalent per hectare per year. The higher critical load, it means more tolerance in the urban area and in this corner of the domain. So compare the result with the earlier study published for Thailand. We see that the range we found is within the range they also found for Thailand. So for nitrogen critical load, so the same approach was applied. And we found that critical load here for nitrogen is from 856 to 5,500 in the domain. And also here we have low critical load in this area. And this is because the topsoil in this area is dominated by sandy loam. And this area is about 14% of the total area of BMR. And our range of critical loads actually found actually within the range, very wide range, found by Park 2002 for South Korea.
Professor Kim,
yes.
If you need to leave at sorry, was it 1400 UTC? It's about 5 minutes to go. If I don't know how much longer, I don't know how much when you need to leave, but obviously if you could leave.
More time. I will finish.
Okay, thank you very much. If you could leave some time for some questions, that would be appreciated. Thank you.
And the sample deposition I showed earlier, right? I showed earlier, but here in different units, that's all. And when we overlay, okay, accident map. So accident is acid deposition minus critical load. And we see that in this corner, we have accident of nitrogen deposition. And for sulfur deposition, we don't find any area that have exceed critical load, meaning that this area is vulnerable to acidity from nitrogen deposition and eutrophication and other actually effect of nitrogen deposition on ecosystem. So in summary, so when we talk about emission of pollutant and greenhouse gases, we talk about the impact on air quality, deposition, soil and water quality. We talk about health and ecosystem, material impact, and our focus was on ecosystem impact. So now, when we look through of that, if we control the emission, we could actually provide multiple effects. And the study actually aimed at providing the science-based information about multiple benefits to air quality, water quality, ecosystem, crops, and climate. The key message here is atmospheric deposition causes substantial effect on the ecosystem directly by phytotoxic air pollutants like ozone I mentioned earlier, and through acid deposition. Asia is a global hotspot of acid deposition and have potential effect on ecosystem. Asia is also the largest emitter of acid rain precursor, and there is increasing trends in several regions. Reduction of atmospheric emission from key sectors such as thermal power plant, industry, transport would bring in multiple benefits. And for that, we also need to, because acid rain, acid deposition is regional phenomena. So we need regional and international collaboration to deal with children. So thank you very much, and I would like to acknowledge my colleagues, staff, and students involved in the deposition project, SIDA for the financial support, and Shamanet, Stockholm Environmental of Asia for the coordination.